Tiange, what are you doing?
I'm feeding my gut microbes with resistant starch.
What is resistant starch?
Resistant starch is a type of fiber which is broken down by our gut microbes. And to better understand this fiber microbial interaction, we categorize our carbohydrates into 4 groups. The first group is HAS. For example, simple sugar is fully digested in the upper gastrointestinal tract. Second, HAC, such as resistant starch, is partly digested in the small intestine, and the rest will go to the large intestine, where gut microbes can break it down and produce short-chain fatty acid, for example, butyrate. Butyrate is absorbed by the gut epithelium, providing energy and promoting blood supply to keep the tissue healthy. The third group is MAC. For example, inulin. The digestion is fully dependent on the microbes in the large intestine, also providing short-chain fatty acid beneficial for our tissue health. The last group is indigestible carbohydrates, such as cellulose, which cannot be degraded by us or by microbes. Within these 4 carbohydrate groups, the benefits of microbial fiber interaction relies on HAC and MAC, which are commonly known as prebiotics or fiber. But what type of fiber and how much do we need to benefit the gut microbes in order to promote our health? So our first aim is to study how the proportion of different types of fiber shapes the gut microbial community. And we hypothesize increasing one type of fiber will promote the growth of the bacteria utilizing this fiber as their food source. Does it mean you only eat fiber and nothing else? No, we need other food components as well, such as protein and fat, and the total energy density is important as well. So our second aim of this study is to look at the fiber microbial interaction within the context of different protein level and energy density, and we hypothesize this protein level and energy density difference will impact our interaction as well. To achieve these aims, we designed 40 different diets. We start from a low protein, high carbohydrates pizza with a lot of sauce and tomatoes topping. We then add different fiber components in the pizza base to change the HAS to HAC to MAC ratio. To reduce the energy density, we replace half the pizza with indigestible cellulose. To make a high protein, low carbohydrates pizza, we switch the topping to pepperoni with different fiber proportion in the pizza base. We added cellulose again to reduce the energy density. Due to the time limit, I will be looking at this 8 diet. Each diet was given to 3 mice in one cage lasting for 5 days. We collected their fecal sample at day 3 and day 5 on this diet. The mice was given standard chow for 1 day before switching to the next diet. To study the gut microbes, first I need to do DNA extraction. I used homogenizer to break off the cells and release DNA. I then added binding matrix to attach DNA. After several washing, I eluted the fecal bacteria DNA. When the primates arrived, I did qPCR on the specific 16S gene on Bacteroides and Faecalibacterium prausniziae, and also universal gene on all bacteria as a reference. I then used the delta CD value to measure the relative abundance of Bacteroides and Faecalibacterium prausniziae. If we only look at the protein to carbohydrates ratio of the diet, ignoring other factors, we found low protein, high carbohydrates diet has a higher relative abundance of Bacteroides than the high protein, low carbohydrates diet. So, in high protein diet, Bacteroides are outcompeted by other bacteria that have more advantages in utilizing protein. Let's have a closer look at the high protein diets. When the food energy density is low, high MAC diet has a lower relative abundance of Bacteroides than the lower MAC diets. This is because Bacteroides mainly utilize sucrose and resistant starch as their food source, but not MAC. So a high MAC diet will starve Bacteroides. Other bacteria utilizing MAC better will outcompete Bacteroides. However, this reduction of bacteroides due to the high mic proportion is not seen in the high energy density diet. This means the energy density of food also impacts the fiber microbe interaction. This can be explained by with no cellulose in diet, mice have larger amount of digestible components available in diet. This includes sucrose and resistant starch, which can be utilized by bacteroides. Therefore, you not only have to feed your microbes with the right type of fiber with the right proportion, but also the other food components you're feeding with, such as protein and energy density, matter as well. For Faecalibacterium, my qPCR results showed the abundance was close to zero. Andy's normal lunch includes a small piece of honey soy chicken and a large amount of vegetables with brown rice. This is similar to our mouse with high protein and low energy density and high fiber diet, so he is starving his bacteroides. Alison is often found at desk eating chocolate, so she had a low protein, high carbohydrates diet. Therefore, she has a high abundance of bacteroides. But how is this associated with health outcomes? To answer this, we need to further look at the interaction of the diet and other bacterial species, and also the mice metabolism, physiology, and immune function with a long-term diet.
How are you today? Doctor, I'm still not feeling very good. Let's have a look at your fecal sample. Here you go. Thank you. So first, we do a DNA extraction on the fecal sample. That's the DNA. And now we do a qPCR. So this is your qPCR results. The result showed you have really low level of bacteroides in your gut, which means you need more fiber